Welcome to this video presentation on convective heat transfer. Today we'll be working through example 2, which focuses on estimating heat loss from a high pressure steam pipe. Let's dive into the problem statement. We have a horizontal high pressure steam pipe with a 10 centimeter outside diameter. This pipe passes through a large room where both the walls and the air are maintained at 23 degrees Celsius. The pipe's outside surface temperature is 165 degrees Celsius and its emissivity is 0.85. Our goal is to estimate the heat loss from this pipe per unit length. To assist us, we'll use the provided correlation for the film coefficient, which is shown on the screen. This correlation involves the Rayleigh number, denoted as RA, which is also defined on the slide. We'll also be using the given properties of air, including its thermoconductivity, kinematic viscosity, thermodiffusivity, Prandtl number, and thermal expansion coefficient. Now let's begin with the solution by listing the given parameters. We have diameter 10 centimeters, which is 0.1 meters. The ambient temperature TA is 23 degrees Celsius. The pipe surface temperature TS is 165 degrees, and the emissivity epsilon of the pipe surface is 0.85. Now we'll note down the properties of air that were provided in the problem statement. This include the thermoconductivity, kinematic viscosity, thermal diffusivity, and the Prandtl number is 0.697, and the thermal expansion coefficient beta is 2.725 times 10 to the power minus 3 per Kelvin. Our objective is to find the total heat loss per unit length, denoted as Q. This total heat loss is a combination of heat loss by convection and heat loss by radiation. Therefore, the total heat loss Q is equal to the sum of the convective heat loss Q conv and radiative heat loss Q rad. So let's first calculate the radiative heat loss. The formula for radiative heat loss from the surface is given by epsilon times sigma times AS times difference of the fourth power of the surface temperature and the ambient temperature. Here AS represents the surface area. So for a pipe of unit length, the surface area is pi times d times L, where L is 1 meter. Now let's substitute the values into the radiative heat formula. And when we do that, we get a value of 441 watt meter. This is the radiative heat loss for the pipe. Next, we need to calculate the Rayleigh number, RA, which is crucial for determining the convective heat transfer. The Rayleigh number is the product of the Grashof number and the Prandtl number. And the formula is given as shown, where LC is the characteristic length, which for a horizontal cylinder is its diameter. So substituting the values and calculating yields a Rayleigh number of 5 times 10 to the power 6. Now with the Rayleigh number calculated, we can now determine the Nusselt number, Nu, using the provided correlation. The Nusselt number is also defined as Hd over K, where H is the convective heat transfer coefficient. Plugging in the values, we get the Nusselt number to be approximately 23. So from the Nusselt number, We can now solve for the convective heat transfer, rearranging the Nusselt number formula and calculating gives us a convective heat transfer H of 7.2 watts per square meter degree Celsius. Now let's calculate the convective heat loss, and the formula is as shown. Substituting the values which we already have, we find that the convective heat loss Q convect is approximately 321.2 watts, considering a unit length of 1 meter. Finally, to find the total heat loss Q from the pipe per unit length, we sum the radiative and the convective heat loss. So this equals 441 plus 321.2, and we get 762.2 watts. Therefore, the total heat loss is as given, and this concludes our example. Thank you for watching. So like, subscribe, and share.